So this is now the session on pulsed laser radiation part 2. And in this section we will cover the generation of very short pulses down to femtoseconds by a process which is called mode locking. And after understanding what mode locking is and how it works, we will take a look at the limits. How short can we make laser pulses in general? What are the physical limitations of these pulse durations? So if you watched the video on pulsing laser radiation part 1, you remember this picture on the motivation where we plotted the thermal penetration depths versus the pulse duration, and we were able to access domains in time for the laser pulses down to maybe a nanosecond. So this region here is able to be covered by Q switching. However, it is limited to these values here. So if we ask the question, can we make even shorter pulses, shorter than nanoseconds, and what are the limits, then we also could ask the question from the application point of view. If we look at the thermal penetration depths and ask the theoretical question, how short would a laser pulse have to be to penetrate only the distance of 2 atoms, so typically values of a tenth of a nanometer, an angstrom. So this would be the region down here, and if you look at the corresponding time domains, you will see we are in the area of 10 to the minus 15 seconds, femtoseconds. Femtoseconds cannot be imagined anymore. We have no picture of what a femtosecond is. And therefore, let me try to give you an analogy. You know that the light travels the distance from the Earth to the Moon in about 1 second. If you now translate this distance to time with the speed of light, so 1 second is Moon to Earth, a femtosecond will be less than the diameter of a hair. These are dimensions which cannot be imagined anymore, at least not for me personally. But the fascinating thing is we can generate them and we can use them, and we can indeed generate extremely precise ablation processes using these femtosecond lasers. So to remember, if you Q-switch lasers, we activate the medium, we pump the medium, we generate an inversion, and we block the resonator with a modulator so that we have an increase of inversion up to the point when we open up the resonator, and then we generate the laser pulse. So depending on the time scale of modulation, we then have during the time where we block the resonator, the buildup of the inversion, and if we open up the resonator, then we get the laser pulse. This is a non-stationary pulse generation. In comparison to that, we can use a stationary pulse generation, and that is we just activate the medium, we pump constantly, we have the modulator, and we switch the modulator such that with each round trip it opens up. You may think of the saturable absorber here as a typical element to be used as a modulator, and then we generate, so to say, pulses from a continuous pumping mode without changing the population inversion in time, but we just modulate a coherent state in the resonator and have a oscillating energy pulse, photon energy pulse in the resonator, which then, if we couple out a certain percentage, will generate a chain of laser pulses of rep rate, which corresponds to the round trip time of the resonator. So as a consequence, we now will have a saturated constant inversion, and a modulation which allows the laser pulses to be outcoupled in a continuous, quasi-continuous mode with a separation which corresponds to the round trip time of the resonator. How do we do that? Well, mode locking has to do with modes, so let's take a look back to the eigenmodes, the longitudinal eigenmodes in a resonator. So not all frequencies are allowed to oscillate in a resonator. Here's a brief sketch of the lowest modes, the lowest orders of the modes. You see here one where we have one full wavelength, the blue one, as a standing wave in the resonator. This is the theoretical limiting case of full reflection. As soon as we have some outcoupling, this will change physically, but in the theoretical limit, these pictures are used. And you have to realize that that is an oscillating electromagnetic field. So it's like in the mechanical picture, the rope between two fixed points where you have this oscillation. And one state is this one. And after half a period, we will have this one. The same holds for the next mode, which now is 3/2 of a standing wave. So we have 3 modes of oscillation in the resonator. So the picture I'd like you to see is that a standing wave has an oscillating electromagnetic field and some nodes depending on the mode of the longitudinal eigenfrequency. So here are plotted a few modes. You see the lowest one is half a wavelength, the next one is 1 wavelength, the red one. The next one is 3/2 of a wavelength, 4/2 of a wavelength, and so on. So there is an unlimited number of modes allowed, and the spacing of these wavelengths, then in the wavelengths domain, they of course are not equally spaced. However, if we translate this to the frequency space, then the difference of the frequencies allowed in a resonator are equally spaced, and the spacing of these frequencies is c over 2l. c, speed of light, l, the length of the resonator. So if we now plot these equally spaced longitudinal eigenmodes in a frequency space, it's very simple. You result with the single lines seen here with the equal spacing. So those are the allowed frequencies in the resonator. And now we also drew into this curve the amplification, the gain curve of the medium which we have in the resonator. And you see immediately, depending on the threshold, we get a certain number of longitudinal modes which are allowed to oscillate in the resonator when they are above the threshold. So now the idea of longitudinal mode locking is a superposition idea, like we have it in space in the case of diffraction at a grating. Then we know that a certain superposition of contributions of diffraction leads to an interference pattern in space. Now it's the same thing here. So you may associate the spacing and the different longitudinal eigenmodes as lines in a grating. So the result of superposition of these individual contributions to the final form of the state of light in the time mode will then be a peaking, like a temporal interference of the eigenmodes. If we take a closer look on how that works, it is the superposition of longitudinal modes, and this superposition can be heard. And as an analogy, we use the acoustic world. So if you look at an acoustic tone, which in this case here has been chosen of half the frequency of the concert pitch, which is 220, respectively 440 hertz. So at this tone, if you listen to it, it is a single frequency tone. So if you take a slightly different frequency of 221 Hertz, then the tone will sound a little different. It will be a little higher. Again, the 220 Hertz. And the 221 Hertz. Now what happens if we superimpose the two sounds? And then, of course, we get a mix of the intensity, and the result will be what you know as mode beating. It will be a change of intensity over time, and you can listen to it. So you now see here the oscillation of the energy in time, and remember the analogy of a diffraction at a grating, which results in spatial interference. So this now is, so to say, temporal, in this case acoustic interference of coherent waves. And the beating frequency is just the difference frequency of the two generating waves. So in this case it is 1 Hertz. Listen to it again. So in the next picture, the same situation is displayed, just with a different example. So again, we have the starting tone, and now we superimpose it with a little different tone. In this case, it is 222 Hertz. So as you remember from the previous slide, now the beating frequency should be 2 Hertz, because the difference is 2 Hertz between the two starting frequencies. Now it is the frequency of 2 Hertz, or the time of the envelope is ½ second. So now, knowing these principles, we can superimpose 3 waves. So say 218 Hertz, 220 Hertz, and 222 Hertz. And the result will be a mode beating again. However, we only will have the full constructive interference of all 3 at a point in time, and in between 2 of them will be in resonance. This will result in a mode beating where again we will have the general maxima, however a few sub-maxima of smaller intensity. You can listen to it. Or if we superimpose now 5 waves of 216 Hertz, 218 Hertz, 20, 22 and 24, we get a corresponding picture. Again, the superposition of these waves lead to a maximum when all 5 waves are in phase, and then the amplitudes add up to the 5-fold value, and in between the minor maxima, as you can see, get relatively smaller and smaller, and you can listen to that as well. So of course what you hear are the values of the intensity, not the value of the amplitudes. The amplitudes oscillate positively and negatively, but the intensities, of course, only are positive. So it is the square of the amplitudes. This holds electrically as well as for the acoustic example. And if you look at it, you see here now the amplitudes squared of the resulting wave. So that is now the intensity. And for a certain, for 2 waves which are superimposed, you can see the values plotted here. If we add 3 waves, you see already that the maximum is even higher. It is the square of 3 times the individual amplitude. And in the amplitude square domain, the intensity domain, of course, this scales with the square of the number of modes which are superimposed. So from the electrical field point of view, or the amplitude point of view, we get at 3 waves a 3-fold value, at 5 waves a 5-fold value. However, if we plot the amplitude square, the maximum value of the intensity scales with the square of the number of modes which are superimposed. So on the other hand, with respect to the pulse width, you also can see here the result of superimposing more modes. If we superimpose 2, the pulse width of the resulting peak is rather large. If we superimpose 5, it gets smaller. Now this pulse duration of the mode-coupled pulses scales linearly inverse with the number of modes. In other words, here we have 1/5 of the original pulse length. Here we have half of the original pulse length. Now, if we keep on scaling, we have here an example where we superimpose 21 waves. So you see in the graph down here already that the sub-minima get smaller and smaller. The peak scales, as I said, with the square. This is again is the field, so it scales linearly with the field, but the intensity scales with the square of the number of modes. So at 20 modes, we have 400 times higher intensity compared to the individual values of the contributing waves. And the pulse duration scales with 1 over the number of modes, so it gets shorter and shorter. If you listen to that, you already can hear this effect. Higher intensities, shorter pulses. And in the limit, we made the example for about 100 waves, 101 waves are superimposed. And again, you see the picture. So now the sub-minima almost vanished completely, and we only get all the energy modulated in time in peak pulses, which, as I said before, are scaling with the square of the number of modes coupled. So if I now turn on the sound, you will, so to say, hear already a femtosecond laser. So after this acoustic example, we now take a look at another way of visualizing this superposition of modes and this starting in phase, that all modes start in phase. However, due to the slightly different frequency, the propagation will mix up and the interference will be more or less random until the point when they really come back again to an in-phase moment, and then all of them superimpose additively again. So another visualization is with pendulas. Imagine a line of pendula, and each of the pendulum has a slightly different eigenfrequency. Now, if they start all at the same time, they all will swing homogeneously. If the frequencies differ slightly, after a few cycles, we will see that some of the pendula will be already further down the road, while others will swing slower. So we have a wonderful video which we will show you here, and you can see the beginning of all frequencies in phase, and then due to the slight differences of the frequencies, we will have the more or less completely destructive superposition, interference, and then Here was a sub-maximum when some of them were in phase, and this now is, so to say, half of the period when they are completely out of phase, and then the whole thing goes on, so to say, reversely. Again, a sub-maximum back to the point when all superimposing frequencies are back in phase. And when they are back in phase, the superposition will be constructive, like at this point, and we will again have a peak pulse in energy. So the trick now is to superimpose these longitudinal modes coherently, so that we really start all of them at one point in time. Then we can manage, as you can see in the display here, that at a certain point in time they all will superimpose constructively, they will interfere constructively, we will have the femtosecond peak which we want, then we will have the mixed destructive part of superimposition, and then again after one period, one round trip in the resonator, the next peak. If we do not couple these modes coherently, in other words, if we allow them to start arbitrarily at any point in time, we will get something very similar to noise. We will just get a superposition of statistical result, so not really something we can make use of. Again, if we superimpose, in this example here, 100 sine functions of equidistant frequencies, they have the same phase for all modes, then we get the mode locking. And if we have arbitrary phase, of course, then we get something which is more or less noise. So now then, how do we switch the modes such that they are emitted at one point in time? And the answer is obvious. If we again look at the resonator, we have a switch in here. Think of a saturable absorber. And the switch allows only from a certain intensity level on the pulses to go through. So those modes who are not in phase with this main pulse will be blocked. However, if they then again start to oscillate due to the gain in the active medium, statistically, more or less all of them, sooner or later, will contribute to this peak pulse. So in switching intracavity, we modulate the losses with one round trip frequency, and thus allow the individual pulses to form, and so to couple all of these modes coherently. And then with a certain transmission in the resonator, with every round trip we get one femtosecond laser pulse. Now if you look in more detail how the mode locking works, we can look at this effect from a different point of view. Physically, if you look at an electromagnetic wave, it just oscillates at a certain frequency. Here the amplitude is displayed, and the formula you all know is the classical wave equation. In frequency space, a single frequency electromagnetic wave, of course, corresponds to a single value. Now what happens if we modulate such a wave in amplitude? This is sketched here. So we modulate the amplitude of that single frequency wave with a certain frequency. This modulation frequency then generates sidebands in the spectrum, which you can see displayed here. And there are two further frequencies in this spectrum, and that is of course related to the modulation frequency omega, capital omega. And we have two bands because it can be an addition or a subtraction to the main carrier frequency, omega n, small omega n. So we will have side bands to the main frequency which are separated to the main frequency by the modulation frequency. And the important characteristic of these sidebands is, of course, that they are in phase with the original mode. And now in this picture, if we apply the modulation of the amplitude, we get sidebands, and these sidebands are, of course, separated from the main mode frequency with, as I said, the modulation frequency of the amplitude. And now, if we choose the modulation frequency to be exactly the frequency of the spacing of two longitudinal modes, you see the effect of dissipating energy from a single mode to the sidebands, which again now are in resonance because the modulation frequency is exactly the frequency spacing of the longitudinal modes. In other words, now we will have the effect that the sidebands will dissipate energy in phase directly into the neighbors of the modes. And this will happen for all modes if we modulate all modes with the round-trip frequency of the resonator. In doing so, we, so to say, couple actively the individual longitudinal modes by modulating the amplitude of all modes with the switch in the resonator. At each round-trip time, we modulate the amplitude, which results in neighbor frequencies exactly at the spacing of the frequency difference between two longitudinal modes. This is displayed here with an active attenuator. You can use an electro-optical crystal or an acousto-optical modulator. Also a saturable absorber will work, but this switch guarantees that all the modes will be emitting coherently, and so they can be coupled coherently and we get the mode locking. If we modulate with some arbitrary frequency again, we have not the resonance case. If we modulate with the round-trip frequency, we get the direct dissipation of energy from each mode into its neighbor modes. So besides acousto-optical modulators and electro-optical modulators, we also can use passive modulation, like the saturable absorber, which I explained before. And the real nice thing about the passive modulation is that now we get an automatic modulation with the frequency of the round-trip time, because automatically whenever the peak power pulse appears at the attenuator, it opens up because intensity is above the threshold, and then all other stimulated or spontaneous emissions will be absorbed and thus not cultivated for oscillating in the resonator. So this is a very elegant way to very simply allow the modulation of the modes. If we look at the limits of how short can we make a pulse, of course immediately it is clear. If we look at the pulses, we will have a certain number of oscillations of the frequency of the light, and logically, I mean, if we reduce this time such that we have not even a full cycle anymore, then we will have not really a laser pulse. We will have some burst of an electromagnetic field. So to talk about a pulse, a laser pulse, we at least need a few cycles of the light. So this is displayed here. So in frequency, then this of course depends inversely to the time domain. So if you look at it from the Fourier point of view, a rather long pulse will correspond to a rather narrow frequency spectrum, and vice versa. if we increase the frequency spectrum, we get shorter pulses, narrower superposition in time. So the spectral width corresponds with the time of the pulse, with the pulse duration directly, very simply. And if we ask the question in the limit, can we get even further down to shorter pulses, then, yeah, you remember the discussion of the number of cycles, and immediately you come to the answer, if we want to have shorter pulses, we need shorter wavelengths. Because then again, if we have only a few cycles, we will have again shorter times. So the answer to how can we generate attoseconds, of course, if you remember the discussion on the number of cycles, immediately tells us we need to shorten the wavelengths. And how can you shorten wavelengths? This can be done by harmonic generation, second harmonic, third harmonic, 10th harmonic, 50th harmonic generation, so we can shorten the wavelengths in nonlinear media as shown here in a jet, in a plasma jet, which we excite by a laser and pump it very hard with high intensities, and the limit of the intensity then defines the harmonic which we will get out of these nonlinear effects in matter. So you can think of maybe up to 50, 60 harmonics, which is then again a lot shorter compared to visible light, which we use to ignite these effects. So that is how we can reduce the wavelengths about by a factor of 50. So then we get close to the attosecond domain. So lasers are fascinating. Pulsed lasers are even more fascinating. And if we ask the limit in precision of addressing single atoms in terms of the thermal penetration depths of laser light, we end up at domains of femtoseconds. In reality, picoseconds, sub-picoseconds are sufficient for most of the materials processing applications, because we have an optical penetration depth, which is in metals about 20, 50 nanometers, so it doesn't make sense to use pulses which result in shorter thermal penetration depths compared to the optical penetration depths. Nevertheless, these lasers allow us to access a totally new domain of materials processing, that is, so to say, photonic milling. We can ablate material at extreme precision with submicron melt formation. So as a consequence, we can reach a new materials processing domain with extreme precision.